It's a little bit early to start talking about this area under the curve, but with our rearrangement of putting chapter 2 now, where we ask the question, how do we measure speed? This is a good time to look at this, because this is just going to come at things from the other direction when we get to this third question, or this third bullet point, how it relates to what else we do. So while you're working on calculating speed, slope of the tangent line, we want to introduce the idea of area under the curve. Specifically, we want to talk about how we think about area and what we're trying to accomplish, how we're going to accomplish that, how we're going to model the continuous with the discrete, and then how we can calculate that. So those are the elements of the things that we're doing. How we think about things, how we calculate things, why we care. So let's remind ourselves of what we're actually looking for. What we're looking for is the area under a curve, what we're finding. What we want to find is the area underneath a curve and above an interval. We want to calculate the amount of space between two one-dimensional things. That's going to give us a two-dimensional area. So I want to calculate above the interval from A to B. There's an interval down here. And under this curve. So we want to calculate the area under the curve and above the interval. I want the area under the curve, which we're going to model with a function to make our lives easier at the beginning. We want the area under a curve and above an interval. So how much space is this taking up? That's what we care about. So this is what we want to find. The tool that we have to find this is just the basic idea of area. To find an area, we have some length and some width, and we just multiply those two things. Area is equal to length times width. So in the tools available category, the only thing that we have to start from is the basic idea of area. Area is equal to length times width. This is just the base idea of area. This is what we mean by area. There's some horizontal distance, there's some vertical distance. We just multiply those two things together. We have a lot of niche formulas for area. A circle is pi r squared. A triangle is 1/2 base times height. But they're all to calculate the same thing. How much horizontal space multiplied by how much vertical space. If the length and width are both constant, then our life is easy. We're just looking at a rectangle and we get to multiply. I spelled C wrong. This is what we want. If the two factors are constant, we get to multiply. This is when life is easiest. If I have a constant 5, over an interval that has a width of 3, then our area is just 5 times 3. I just take the height and multiply by the width. If the length and width are both constant, then we get to multiply. This is our favorite. This takes us back to nth grade, where n is the number of the grade where you learn that area is equal to length times width. I probably should know what that is. I could probably look up what that is, but I never remember to do it at this point. If the length and width are both constant, then we get to multiply. Let's remember what multiplication is. Multiplication is addition when all the terms are the same. Multiplication is addition when all the terms are the same. So when I write 5 times 3, I mean 5 plus 5 plus 5. I mean 3 5s. Since all the terms, the 3 5s are all the same, I get to summarize by saying 3 times 5. Times table is like a big list of shortcuts that we have to remember. If the terms are different, then we're kind of stuck with multiplication. So multiplication is addition when all the terms are the same. If the terms are different, then we stick with addition. So if I got 3 different terms, 4 plus 5 plus 6, as it stands, I don't have 3 of anything. So I just got to do 4 and 5 is 9, plus 6 is still 15. It's not 3 times anything. When we think of this and translate it back to our area problem, we multiply when we can. So this would, if we translate this back to an area problem, that way, that way. If we translate this back to an area problem, we'll just multiply when we can. So this represented as an area problem. Let's multiply. So taking this and translating it back to an area question, we can multiply on the flat parts. As long as we have just a constant length multiplied by a width, then we can multiply. And that's what we want. If we multiply on the flat parts, then we can add the results. So thinking in terms of the graph, if I've got a 4, a 5, and a 6, each of those is going to be over a unit of 1. Let's just put ones down here. I just make this 3 rectangles. So I've got a 4. Each of these is going to be a 1. So instead of having 3 5s like I had before, I've got 1 4, 1 5, and 1 6. It's an addition problem. On the flat parts, each of those areas is a multiplication problem. I do 4 times 1, plus 5 times 1, plus 6 times 1. I've got 1 4, 1 5, and 1 6. Instead of 3 5s. So I multiply on this first rectangle, then I multiply on the second rectangle, then we multiply on the third rectangle, and we get our area that way. Any questions? Of course not. This is multiplication and addition. We all understand multiplication and addition, theoretically. The complication we have now in calculus is the same complication that we always get in calculus when something is continuously changing. We're trying to create a model for continuous change, and everything that we think about is in discrete changes. We need to create a model for continuous change, but our calculations are in these discrete changes. We can't add over a continuum because there's nowhere to put a plus sign. There's no next real number. We're creating a model for continuous change with discrete change. So the problem that we run into is the same problem that we made calculus for, continuous change. The problem that we run into here is that we have a function changing continuously. In the previous problem, we can multiply on the flat parts, but in a continuously changing function, there are no flat parts. when the function does go flat, when the derivative is equal to 0, for example, that happens at exactly 1 point, and immediately after that, it's not flat anymore. The width where that function was flat is 0. So the area there is 0. That's kind of a problem because we know that there is area here. We could see that. I colored it in with the blue pen. If the area was 0, I wouldn't have been able to cover it with the blue pen. So we know there is area. Problem is there are no flat parts, so we don't get to use our multiplication. The problem with continuous change, the other problem that we run into is that there is no next real number. So there's nowhere to put the plus signs. That's the continuous problem. There's no next real number. Nowhere to put plus. If you name a real number, there is not a next real number. It's a different kind of infinity that we're dealing with. Our solution to this problem of continuous change is the same solution that we always apply in math. Kick it back to an older problem. Send the problem back to a lower court. Well, we have this continuous change. There's nowhere to put the plus. There's no next real number. So we just make that happen. Same solution we always do. Go back to the previous problem where we can do these things and approximate the continuous. Go back and approximate. Our solution to this problem is to go back and approximate. We're going to model our continuous with a discrete. Use the discrete to model the continuous. Questions? How's everybody? I goofed off yesterday and I said today that we were going to talk about area under curve. So here we are. Not goofing off, talking about serious business. I'm doing it very seriously. This is my serious face. That's how you know I'm serious about this. We're going to use the discrete to model the continuous. I want to calculate area. Area is equal to length times width, but the stupid length is all continuously variable. That's the problem. Problem says find the area. We're like, oh, no problem. Area is equal to length times width. Then we look at the area we're trying to calculate. We're like, ah, dang it, stupid length is all continuously variable. So we're going to exploit that continuously variable part. Since the function is continuous, wherever we're looking here, that function is continuous. If we look close enough, the function isn't going to change that much. If we look at a small enough interval for x, the function is not going to change that much. If we look close enough, the function isn't changing that much. That's the idea of this. That's the idea that we're going to use for this continuously part. Because our function is continuous, if we look close enough, f doesn't change that much. Right now, we are standing on a very large spheroid. It's round. But when we look outside, we say, no, that shit is flat. That is because we are looking very closely at the spheroid that we're standing on. So because we are so small compared to what we're standing on, it looks flat to us until we got a long enough view. But it's also bumpy enough that we can't see very far until you go to the Midwest. I gotta tell you, if you spend your whole, if you go all the way to being an adult before you go see the Midwest and how flat it is, it's very weird when you fly into Chicago. You're like, oh, this is like creepy. It's like the country didn't render at some point. Like when you're playing a video game, you get to a spot and your computer's like having trouble, and it just like can't render the stuff around you, and so you're just on this blank flat plane. That's what it's like flying into Chicago. If you look the opposite direction of the city. You know what I mean? It's weird. If you look close enough, the function doesn't change that much. That's the continuous part. Now, if the function is not continuous, that could mean that if we have a jump discontinuity, that means in no time that the function has a jump, in that no time, in that no change, the function radically changes its value, right? That's why we need that continuous change. Or if there's a vertical asymptote, then one side the function is going towards infinity, and maybe the other side the function is going to negative infinity. We are radically changing values. But if we have a continuous function, that's not going to happen. So that's what we're going to do. We're going to use the fact that if we look close enough, the function isn't going to change that much. We're going to make an assumption that the function is constant for intervals so that we can multiply. So we make our assumption. We're going to assume that f is constant for some small change in x. Because I actually want to draw this, I'm going to use gigantic changes for x. But I'm going to say, here's a delta x. There's some small change in x. Here's some other small change in x. I know it looks gigantic, but remember, we're looking very close. I just forgot I need some of these to be. Now on each of those small changes in x, we're just going to choose a value for the function. I'm just going to pick a point, say x1, and evaluate the function there. And say, whatever that value of the function is there, that's what it's going to be for that whole delta x. So mechanically, we choose a value from each of these intervals, evaluate the function at those points. We're going to evaluate the function at some point from each of the small changes in x. That will be the value of the function for the entire change in x. Now that we've flattened out the function, at least in pieces, and then I'll go on to the next one and choose a different value. You know, like an x2. I'll just evaluate the function there. And instead of having the function have all this change, I'm just going to flatten this out. And then I'll pick another point, x3. Evaluate the function there. And instead of having this continuously changing function, just flatten that out. Because I'm not really going that far from the function because I'm looking at a small interval delta x. So now I'm just looking at a low resolution version of this continuously changing function. Now we just calculate one area here, and another area here, and a third area here. Now it's 3 rectangles. Now I've got these 3 rectangles, area 1, area 2, and area 3. And they're just going to be each of these different lengths. Multiplied by our width. And then we just add them up. And that's our approximation. Starting to regret trying to stay true to the color scheme. All right, almost done. All right. We take this continuously changing length and model it with a discrete changing length by making it constant on small intervals. Then calculus enters the chat. We improve our approximation by using more intervals, a smaller delta x, using more rectangles. Once we find out how we're going to improve our approximation, we just do that forever. This is the whole idea. Now you might realize I've done a version of this same talk before. That's because I'm going to do another version of this same talk later this semester. Next semester, if you are unfortunate enough to be stuck in my Cal 2 class, first of all, my sympathies. And second of all, yeah, I'm going to do this again at the beginning and then somewhere near the start of the beginning. And then if you're really unlucky, if you really are unlucky, you end up in my Calc 3 class, guess what happens? Oh, no, it's deep, it's back here. What happens is the same thing. Same thing. Only we upgrade to a function of two variables. So instead of area under a curve and above an interval, it's going to be the volume under a surface and above a region. But the thinking is going to be the same. I'm going to take this bumpy surface and I'm going to flatten it out over little rectangles. And then I'm just going to make those rectangles smaller. Then I'm just going to use infinitely many rectangles. And it's the same thinking. Moreover, the same calculation. The hard part is telling the integral what values to plug in, but that's a problem for a later date. Any questions? How's everybody okay? The takeaway that we want here is that we're doing the same thing. We're doing the calculus thing. We're modeling continuous change with discrete change. There's this gulf between the discrete and the continuous that we have to think our way over. We can only think our way over. We create a model with the discrete, and then we try to just keep refining that model until it looks continuous enough in our eyes. If we run out of computing power, then we just like take our contacts out and everything gets kind of blurry. And it's like, oh, good enough. You know what I mean? Like the reason that pixelated pictures look so bad on your computer screen is that the resolution is too good. Those original pixelated pictures that you saw, they were originally on CRT screens. And CRT screens look shitty, so you couldn't tell that it was that pixelated. But now that we have like high resolution and high definition, you look at like Super Mario World and you're like, oh man, this looks terrible. And that's because you're looking at it too clearly. When you look at all fuzzy like we did back in the 90s, it looked great. Any questions? When I originally drew this function, I was like, oh, high definition. Not 4K, because I'm not going to buy that much of a camera. I mean, it's like 720. So. But I mean, look how badly I went like I went past even like Game Boy. This is like Atari 2600 area. You can see like these big gigantic squares. Does anybody even know what Atari 2600 is? I'll bring in my Atari 2600. You can see how bad 80s gaming was. And I go, oh yeah, retro. It's like, oh no, that was awful. No, it was bad. I mean, at the time we were like, oh yeah, look at this. I don't have to spend a quarter to play a video game. It looks like shit, but you know, so do the arcade games. Any questions? Comments? Slide them in. I can't remember exactly when Pong came out, but we have progressed from Pong to like the shit we have now in like one person's lifetime. That's insane. Especially when you can get the game that you want to play now, those fancy, you just like summon it from the ether. You don't have to go to the store and buy like a cartridge and stick it in and then pull it out, blow on it, and then put it back in. Does anybody even know what I'm talking about? No, because y'all are too young. And I'm just playing the old person right now. Man, back in my day, games came on cartridges. And sometimes you had to blow on them before you put them in. And then shove your wallet in the slot to keep it in the proper place. That's a Nintendo Entertainment System thing. All right, so this is the thinking that you want to have. Remember the big picture in calculus? Calculus is modeling how things are, when things are continuously changing. Sometimes people say calculus is mathematics of change. It's the mathematics of continuous change. That's the problem, the continuous change. We model the continuous change with discrete change because the calculations are easier. And we just do that more often. So we'll just do that forever. Do that forever. You can't focus. All right, that's it for today. I will see you all on tomorrow. Everybody have a good day. Think about the discrete versus the continuous, and thanks for playing.